Welcome back. This is Session 9, the Model Zoo. Last time, one law, one architecture, one public recipe, and every lab had access to all three. Today, 5 labs, 5 different models. What you're about to see are decisions, not accidents. So here's where we stand. Every model that reaches a user goes through 4 stages. Pre-training decides what it knows, and 8 sessions in, that stage is behind us. Alignment decides how it behaves. That's next session. Serving decides what it costs to run. And use, that's where the last 3 sessions of this course will live. Now, today's session isn't one of those boxes. It's a cut straight across all 4 of them. 5 labs build models through exactly these stages, and they decide differently at every single one. That's why the framework we're about to build has 5 dimensions and not 1. Because look at what sessions 5 through 8 actually fixed. The transformer block, causal decoding, and the scaling law. 1 bar, under 1 stage. Everything else on this road is still a choice, and this session is about who makes those choices and what each one costs. So what's fixed and what's still open? Let's split it down the middle. On the fixed side, the transformer block itself from Session 5. Causal decoding from Session 7, and the scaling law, C approximates 6 and D, from Session 8. That law tells you how much compute to spend. It doesn't touch anything else. On the free side, which attention variant a lab picks. Whose feedback aligns the model's behavior. Then, the data, what goes in, how open the weights are, and how specialized a model you end up with. And even with a fixed budget, how that compute actually gets spent. 5 labs, 1 recipe, 5 different sets of answers to these questions. Let's make this concrete before we make it abstract. 5 labs took that same recipe. Here's what came out the other end. GPT-4 reasons through problems earlier models couldn't touch. Claude declines requests that GPT-4 will complete. Gemini reads an image the instant you hand it one. LLaMA ships its weights openly. It runs on a laptop. And DeepSeek was trained at a reported fraction of GPT-4's cost. Same law, same architecture, same public recipe. So whatever pulled these 5 apart, you can rule out the recipe. So if it's not the recipe, what is it? Look at what you just saw. 5 labs, 1 recipe, 5 products that behave nothing alike. Those differences aren't accidents of scale. They're decisions. And so far, we haven't named a single one of them. Every one of those decisions falls into one of 5 categories. That's the framework the rest of this session builds. Here's what you'll walk away with. Given a model's architecture flags, you'll be able to explain what problem each specific decision solves and what it costs. You'll be able to name the alignment approach behind GPT-4, that's RLHF, behind Claude, that's constitutional AI, and behind DeepSeek R1, that's GRPO, plus who introduced each one and what it assumed. You'll be able to place any current model family on the 5-dimension framework using only its published model card. You'll be able to explain why a growing KV cache, not parameter count, is the specific problem GQA and MLA solve, and compute the reduction either one buys. And you'll be able to tell training time compute scaling apart from test time compute scaling, and name one family's choice on each axis. 5 products is a lot to hold in your head at once, so let's build the one tool that makes it manageable. To compare 5 very different systems fairly, ask each one the same 5 questions. Architecture. Which attention variant did they pick? Which position scheme? Dense or a mixture of experts? Alignment. Whose feedback shapes the model's behavior? Data. The corpus mix, the tokens, the quality? Openness. Open weights or a closed API? And specialty. General purpose, reasoning focused, multimodal, or built for the edge. Apply these 5 questions to any family you meet, and the apparent chaos of the model zoo resolves into a map. Now let's put that map on a timeline. 5 families, 6 years of releases. Before the rows land, guess which family you'd expect to move fastest. Watch OpenAI first, GPT-3, then ChatGPT, then GPT-4, then the O1 and O3 reasoning models. Anthropic, Claude 1 through Claude 4, landing every 6 to 11 months or so, up to this point. Hold that pace in mind, because it's about to break. Google, Palm, then Gemini 1, 1.5, and 2. Meta, LLaMA 1, 2, 3, and 3.1, all with open weights. And DeepSeek, V2, V3, and R1, all landing in under a year. So there's the answer to your guess. 5 families, 5 different paces, and DeepSeek moving fastest of all. Before we go further, one naming point, because it trips up almost everybody, and it will make the rest of the session readable. A generation is when a model shipped. A tier is which model of that generation you're actually calling. Those are 2 different things, and the names carry both. Here's the ladder. Anthropic ships Haiku at the bottom. Small and fast and cheap. Sonnet in the middle. Opus at the top, the most capable. Most people stop here and think a tier is just a size. Watch what happens when we ask which version each tier is actually on. Sonnet and Opus are both on 5. Haiku is on 4.5. Look at that gap. Haiku sits a full generation behind, and that's still the current Haiku, not an old one you'd avoid. So I'm using Claude 5 isn't actually a precise statement. It depends entirely on which tier you called. A tier isn't a slice through one generation. Each tier moves on its own clock. And it gets one step stranger. This is Fable, a 4th tier you haven't met yet. It didn't exist in 2025. It arrived in June 2026, above Opus, and it's already on 5 too. So the set of tiers isn't fixed either. New rungs get added to the ladder. Now, a minute ago, I asked you to hold on to Anthropic's pace, roughly 1 generation a year. Here's the number that breaks it. Between February 2025 and July 2026, Anthropic shipped 8 version numbers: 3.7, 4, 4.1, 4.5, 4.6, 4.7, 4.8, and 5, spread across 4 tiers. 8 releases in 17 months, against the roughly 1 a year pace of the generations you just watched. So, when you read Claude in a paper, ask which generation and which tier, because by the time it was published, both had usually moved. Remember this, every chart later in this session names the tier, not just the generation, for exactly this reason. Let's start with OpenAI, and with a genuine surprise. Remember, Session 8's law spends compute once during training. In September 2024, OpenAI's O1 broke that assumption. Here are the 2 tracks, side by side. Training time compute. The law you already know from Session 8 is spent once, before any question is ever asked. You buy it with more parameters, more training tokens. And once training is done, notice that every answer gets the exact same fixed compute. Easy question or hard one. GPT-3 to GPT-4 is this axis, bigger and bigger training runs. Test time compute is the opposite. And here's the twist. It's spent per answer, after the question actually lands. Watch what it does instead. The model works through a longer chain of thought before it replies. Which means harder questions can now get more thinking automatically. You might be thinking, this sounds like it should just be a longer prompt, not a new scaling axis. It isn't. The model itself decides how long to think. Here's the payoff. O1 lands near human level on competition mathematics, the AIM benchmark, purely by thinking longer per answer. That's OpenAI, September 2024, in a paper called Learning to Reason with LLMs. O1 and its open replications made how long the model thinks a second scaling axis, sitting right alongside the one you learned in Session 8. Here's a different kind of decision now. Not how much compute, but whose judgment trains the model. RLHF needs a constant stream of human comparisons, and it gives the model no explicit standard to point to. Watch what Anthropic tried instead. 2 ways to supply that judgment. RLHF. Humans rank pairs of the model's own answers. A reward model learns that ranking, and here's the mechanism. The policy, the model itself, is tuned against it. It needs thousands of labelers on a constant supply. This is what trains ChatGPT and GPT-4's tone. Constitutional AI. Watch this. The model critiques its own answer against a written constitution. You might expect that still needs an army of human raters. It doesn't. There's no standing human labeler pipeline at the harmlessness stage. And the Constitution itself, the actual list of principles, is published. This trains every Claude model since. That's by and colleagues, Anthropic, December 2022. A written set of principles, plus the model's own self-critique, substitutes for human labels at the harmlessness stage. Here's one more family, and a decision about what a model is trained on, not how it's aligned. Why would a lab bother designing for images from day one, instead of just bolting vision on later? GPT-4 gained vision by adapting a text-only model after training. Now look at Gemini, designed multimodal from the very first gradient. 2 ways to get a model that can see. Retrofitted. A text-only model is trained first, the way GPT-4v started. A vision encoder is bolted on afterward. Images get projected into that existing text space. Native, image, and text patches share one sequence from day one. Attention runs across both modalities natively, not bolted on. Gemini 1.5 extends that to a 1 million token context. Now, this one's a data and training strategy decision. No single invented mechanism, no one paper behind it. The 5 methods still ahead of us today are exactly the other kind, and each comes with a paper we can point to. Before we get to Meta and DeepSeek, there's a cost every one of these models pays, quietly, on every single reply. Every token the model generates has to look back at every token before it, and that means rereading every earlier key and value. So, here's the idea. Compute each key and value once, store them, never compute them again. That store grows by 1 entry for every token you generate. Here's the actual size of that cache. Twice the number of layers, times the number of key value heads, times the head dimension, times the sequence length, times 2 bytes per value. Let's put 2 real GPUs on the same chart. An RTX 3090 has 24 gigabytes. An A100 has 80. Now watch the cache itself get plotted for an 8 billion, a 70 billion, and a 405 billion parameter model as the conversation gets longer. Look at that 405 billion line. Its cache alone nears an A100's 80 gigabytes by 128,000 tokens. The cache, not the parameters, is what runs out. That growing cache you just saw is exactly the problem Meta's next generation went after. Meta's bet. Freely released weights accelerate research faster than closed ones, and LLaMA 3 added 2 fixes for that growing cache you just watched. 2 generations, 2 years apart. LLaMA 1 and 2 put the weights out in the open, at sizes from 7 billion up to 70 billion parameters, and you could just download them. Standard multi-head attention, nothing exotic. This sparked the entire open-source LLM ecosystem. LLaMA 3 adds GQA, fewer cached key-value heads than query heads, and ROPE, position encoded as a rotation. 128,000 token context, 15 trillion training tokens. Let's actually look inside both fixes. First, GQA, fewer cached key-value heads than query heads. Then ROPE, watch position become a rotation, not an added vector. Start with plain multi-head attention. Every query head keeps its own private key value pair. So, how many caches does that actually cost you, at scale? GQA groups those query heads. Instead of 1 KV pair each, watch a whole group share 1. The cache now only has to hold 1 key value pair per group, not per head. You might be thinking a shared cache must cost accuracy. And it does, a little. But fewer groups still means a smaller cache, and that trade is worth it. Push that grouping all the way down, and you get the extreme version, shown here on the right. Multi-query attention, 1 shared pair for every query head. 4 times smaller than plain multi-head attention, at the cost of even more shared accuracy. GQA is the middle ground between the two. Now, the second fix, ROPE. Session 5 sinusoidal encoding, remember, adds a fixed position vector to each embedding. Watch what rope does instead. It rotates the query and key vectors by an angle proportional to position. Here's the payoff. Rotate two vectors by the same extra amount, and the angle between them doesn't change. Only how far apart they started does. So the dot product between a rotated query and a rotated key depends only on their relative distance, never their absolute position. Here's why that's worth having. A model trained on conversations up to, say, 8,000 tokens can still make sense of token 50,000. All it ever learned to use was the gap between two tokens, never the raw count. So in one sentence, encode relative distance, not absolute position. And that's what lets a model trained at one length generalize past it. One family left, and it's the one that made the whole field recalculate its training budgets. How does a lab actually train at a fraction of everyone else's cost? DeepSeek entered in 2024, claiming GPT-4 class results at a fraction of the training cost. You'll see 2 more fixes for the cache here, plus a third idea for alignment. 2 models. 8 months apart. Start with DeepSeek V2, a mixture of experts, 236 billion parameters in total, and only 21 billion of them active for any one token. MLA, a compressed, reconstructed KV cache, trained at a reported fraction of GPT-4's cost. DeepSeek R1 adds GRPO, and here's the trick: reward correct answers with no separate reward model at all. No human-written reasoning examples anywhere in the pipeline. And it matches O1 class reasoning at a reported low training cost. Let's open up both of DeepSeek's mechanisms. GQA shrinks the cache. You saw the mechanism already. Group the query heads, and each group shares one cache instead of keeping its own. MLA compresses it further into one shared latent, reconstructed on demand. MLA's first move: watch the hidden state compress down to a small latent vector. Store only that latent, not the full key and value. You might be wondering how throwing away the full key and value doesn't lose information. It doesn't, because nothing is thrown away yet, only compressed. Then, the moment attention needs them, you reconstruct the key and values straight from that latent. So in one sentence, one small vector standing in for 2 full ones. Now the second mechanism, MoE. For every token, a gating network scores every expert in the layer. Watch 2 of those scores light up gold, the top 2. Every other expert's score stays gray. Every other expert stays completely silent for that token. So in one breath, route sparsely, pay only for what you use. That's why DeepSeek V2 can hold 236 billion parameters of capacity, while only spending the compute of a 21 billion model. Let's write down what the layer actually computes. The output is a sum over the top 2 experts only, and each expert's contribution is weighted by the score the gate gave it. So the gate does 2 jobs at once. It picks which experts run, and it says how much each one counts. Before we move on, let's actually compute one of these numbers ourselves. Recall the mechanism. Query heads grouped, sharing a KV cache. Here's the cache size picture again, starting from plain multi-head attention as the 1 times baseline. And here's GQA shrinking that baseline. The example on screen groups all 8 heads into a single group, an 8 times smaller cache. The numbers you're about to get are different. Take a model with 8 query heads sharing just 2 KV groups. What reduction factor does GQA buy here over plain multi-head attention? And how many query heads actually share each cache? Work it out before the next click. Let's walk it through. Plain multi-head attention stores 1 KV cache per query head. With 8 heads, that's 8 separate caches. GQA groups those 8 query heads into 2 groups, and each group shares 1 KV cache. That's 8 divided by 2, 4 query heads per cache. So instead of 8 caches, we're down to just 2. The cache shrinks by that same factor, 4 times smaller. In one sentence, fewer groups always means a smaller cache, in exactly that ratio. Solution: you divide 8 heads by 2 groups and get 4 heads per cache. GQA buys a 4 times smaller KV cache than plain multi-head attention here. At 2 groups instead of 8. So we've got 5 families and a framework. How did the field actually decide who was ahead? For about 2 years, if you wanted to compare frontier models, you used one number, their score on MMLU. Year of release across the bottom. MMLU score up the side. MMLU is a 57-subject multiple-choice exam. And that dashed line you see is roughly human expert performance, about 89%. And here's the picture everyone worked from. GPT-4, Gemini Ultra, Claude 3 Opus, both LLaMA 3 sizes, O1, DeepSeek R1, GPT-5. Notice each point names the tier that was measured. Claude 3 Opus rather than Claude 3, so you're comparing like with like. This is a genuinely useful chart, and you can read it the way the field did. Who's ahead, and by how much. Now let's zoom back out, and instead of looking at the models, look at the ruler we've been measuring them with. MMLU is the exam that defined the GPT-4 era. Almost every model card you've seen today quotes it. Watch what happens to it. Same frame you just read, year of release along the bottom, MMLU score up the side, and the dashed human expert line again, at about 89%. Here's the climb. GPT-3 in 2020 scored 43.9%, worse than guessing on some subjects. 3 years later, GPT-4 scored 86.4%. That's the jump this whole course has been explaining. Now watch the next 2 years. Every frontier model, since 2023, from all 5 families, lands inside this one narrow band. And they're not tied because they're equally good at everything. They're tied because the exam ran out of room. And here's the part I want you to remember. After the middle of 2025, there is nothing to plot. Not because the model stopped improving, but because the labs stopped reporting this number. A benchmark everyone passes has stopped measuring anything. So the field replaced it. GPQA Diamond for graduate-level science, SWE Bench Verified for real code, ArcAGI2 for abstract reasoning. Every score you see here is the figure the lab itself published. And the gap on the right is real. The number simply stops appearing on model cards. Let's slow down on that, because it's a habit worth building. Same chart, full and settled. 6 years, 43.9 to 92.5%. Notice this chart drops the individual names you saw 2 slides ago. Past 2023, the exact model stops being the story. Only a colored key by family remains. And what matters is that every family lands in the same narrow band. So when you read a model card and see a benchmark score, ask 2 questions. Is this benchmark still separating models? And is the lab still reporting it? If a number is quoted everywhere, and everyone scores within 2 points of each other, it has stopped being evidence. One more check, this time on alignment. Recall the alignment card from our framework. 3 real systems, 3 approaches you've now met. Here's how each one actually behaves. Look at System A. It critiques its own answer against a written set of principles, then explains itself in exactly those terms. Now, watch System B. It's tuned directly on thousands of human comparisons between pairs of candidate answers. And System C. It gets rewarded only when its final answer is checkably correct. That's your third and last clue. Which system is RLHF? Which is constitutional AI? Which is GRPO? Match all 3 before the next click. Let's match them. System A critiques itself against a written standard. That's constitutional AI. System B is tuned on human preference comparisons, the classic pipeline. That's RLHF. System C needs no separate reward model, only a checkable final answer. That's GRPO. Solution. You've got A as constitutional AI, self-critique against principles, B as RLHF, tuned on human comparisons, and C as GRPO, rewarded on correctness alone. Let's close the loop we opened at the start of this session. We started here. 5 products, 1 recipe, and not 1 decision named. Now, every one of those differences has a name and a category. You can read a decision from architecture flags. You can name the alignment approach behind GPT-4, Claude, and DeepSeek R1. you can place any family on the 5-dimension framework, and today's lab has you practice it on a real model card. You can compute a KV cache reduction, and you can tell training time compute apart from test time compute. Before we close, one honest admission. 3 names came up today: RLHF, Constitutional AI, GRPO. Remember, we introduced them by what they do, not by how they actually work. 2 paths, side by side. The usual path, RLHF, human-ranked pairs. Or Constitutional AI, self-critique. R1's path. GRPO, correctness, no reward model. Named, not built. That's the one that this session leaves open, on purpose. Here's the road so far. Language, vectors, sequences, attention, the transformer, BERT, GPT, scaling laws. And here we stand, session 9, the model zoo. 5 sessions still lie ahead of you, across 3 phases: foundations, architecture, and the real world. Training and alignment is next. You can now place any of these 5 models on the framework: architecture, alignment, data, openness, specialization. But 3 of those alignment names, RLHF, Constitutional AI, GRPO, were just names. Next session, we open that box and build each one from first principles. In the lab, part 1, you'll pull the real published cards for LLaMA 3, GPT-3 or GPT-4, and DeepSeek v2, and score each one on all 5 framework dimensions, using only the card's own numbers. Part 2, you'll reproduce today's quiz on real numbers, GQA's and MLA's actual byte-level KV cache savings over plain multi-head attention at a real context length. And the challenge: run a small DeepSeek R1 distill model locally through LLaMA and compare its chain of thought trace against a same-size non-reasoning model on the same prompt. You'll watch test time compute actually run, not just hear it described.